Okay, and so now we want to do this problem. So notice we could have multiple issues here. So x could be 0. If x is 0, we're going to have a discontinuous integral. But notice x is bigger than e, so we're OK with that. Also, natural log of 1 is 0. And so we have to make sure we're not integrating over that. So we're not integrating over where x is equal to 1. But we're not because the integral starts at e, and e is bigger than 1. OK, so then this is an improper integral. But the only reason it's an improper integral is because we're integrating to infinity. So then this, the integral from e to infinity, dx over x ln x, this is the limit as r goes to infinity, e to r, dx over x ln x. Okay, and so now again, the strategy is when we're computing these integrals, forget about the limit. We have to keep writing it down, otherwise we're not writing things that make sense. But we're going to forget about the limit and just work on computing this integral. So now let's just work on computing this integral and think for a minute the technique that you would use to compute this integral. I will go ahead and say it in a minute, but pause the video if you want to. Okay, hopefully you thought about it for a little bit, and you would see that u, if you choose u, is equal to the natural log of x. Then du dx is equal to 1 over x. And so this tells us that du is equal to 1 over x dx. And what's going to happen with this integral, this, again, I just have to write out the limit, and then I'm going to do stuff with the integral as r goes to infinity. Okay, I'll change the bounds on the integral in a moment, but I've got dx over x, and dx over x is equal to du. And I've got log x is equal to u, so I've got du over u. Okay, to change my bounds, my lower bound here, if x is equal to e and u is equal to log x, then u is equal to log e, but log e is just equal to 1. And r is going to be natural log r there. OK, so now I want to do the antiderivative of du over u, or to compute the integral of du over u. So this is the limit as r goes to infinity. OK, so the antiderivative of 1 over u with respect to u is the natural log of the absolute value of u, but u is just positive here. So this is the natural log of u, and we're going from 1 to the natural log of r. And if I plug in my limits here, or the endpoints, this is going to be the limit as r goes to infinity, and we're going to get natural log of the natural log of r minus the natural log of 1. Well, the natural log of 1 is equal to 0, and so this is just equal to the limit as r goes to infinity of the natural log of r. Okay, so let's think what's happening here. As r goes to infinity, the natural log of r goes to infinity. As the natural log of r goes to infinity, the natural log of the natural log of r goes to infinity. So this is equal to positive infinity, so we would say this diverges. Let me say two things as an aside. One of the reasons I stress changing the limits when you do u sub is that once we change to u, we don't have to go back to x. Writing things properly gets very confusing, and it gives you opportunities to make mistakes if you don't change the bounds on the integral when you do u sub. The other thing that I want to mention is that this integral goes to, the integral is infinite. I mean, so if you look at the graph of this function, the graph is going to look something like this. But it goes to, the function itself goes to 0 quickly, but not quite quickly enough to make this converge. And it actually diverges very, very slowly. This right here, the natural log of r, is the integral of the function from e to r, and technically it goes to infinity, but if you try putting this in your calculator, see what r has to be for this amount here to be like bigger than 10. Like for the integral to be bigger than 10 even, r is going to have to be almost unimaginably large. So it diverges, but we might say it diverges very, very slowly, and if we want to be sort of imprecise, we would say it diverges very slowly, or it just barely diverges. Anyways, those last two comments aren't as important as the computation that I have here.